Welcome to this explainer. Today, we are diving into exactly one topic, but it's a huge one: NCP-MCI 7.5 4.2 erasure coding requirements and interactions. If you're an infrastructure admin looking to master how EC behaves under the hood on AOS 7.5 and totally crush this section of the certification exam, you are absolutely in the right place. We're going to take this at a steady, methodical pace, dissecting the exact interactions you need to know. All right, let's jump in. Here is our game plan for today. First, why erasure coding matters. Second, a walkthrough with concrete examples. Third, those tricky exam traps and edge cases. And finally, the key facts you just have to memorize.
Okay, let's make sure we're all starting on the exact same page with a foundational definition. Erasure coding, or EC, is a data resiliency feature that fundamentally shifts how your cluster protects information. Instead of taking a block of data and making identical, heavy clone copies of it to spread around your nodes, EC uses mathematical parity information to rebuild that data if a disk or node fails. It's just a more elegant, mathematically driven approach to protection that massively increases your usable cluster capacity.
Next up, we have replication factor, which you guys probably just call RF. This is your baseline data resiliency setting, right? It dictates the total number of copies of your data that are actively maintained in the cluster at any given time. So if your storage container is set to RF2, you've got 2 copies. If it's RF3, you have 3. Now, erasure coding interacts directly with your RF configuration, and as we'll see in just a minute, your RF dictates the absolute minimum hardware footprint you need to even enable EC. And our third core concept is cluster fault tolerance, or CFT. While RF is all about the number of data copies, CFT defines your cluster's overall level of resiliency against simultaneous failures. For instance, a 1n/1d tolerance means your cluster can survive one node or one drive failure without breaking a sweat. A 2n/2d tolerance means it can handle 2 simultaneous failures. As we'll uncover, your configured CFT has massive and sometimes totally hidden implications for erasure coding. All right, Section 1. Why erasure coding matters. So here is a massive point, and honestly, a really common exam distractor. A lot of people think you have to choose between erasure coding and other storage efficiencies. Not true at all. The capacity savings you get from erasure coding are actually in addition to your deduplication and compression savings. They literally stack on top of each other. By using parity information instead of full data replication, you're stripping away redundant blocks. This maximizes the usable, raw space on your cluster, and you don't sacrifice an ounce of data resiliency. You are quite literally doing more with less. Moving right along to Section 2, walkthrough and concrete examples. Let's visualize this. Think about a standard Nutanix storage layout before erasure coding is applied. You've got your primary data blocks, let's call them A, B, C, and D. In a standard RF environment, each of those primary data blocks has a corresponding replica block distributed somewhere else across the cluster, just to protect against a node going down. Now, while this is incredibly safe and super performant for write-heavy workloads, man, does it eat up storage space. You're essentially paying a 100% capacity tax for every piece of data you write in an RF2 scenario, and it's even worse in RF3. But when we enable erasure coding, watch what happens. AOS dynamically calculates an EC strip, which is just a combination of data and parity. It takes those original data blocks, does some math, and computes a single parity block, which we'll call P. Then it goes in and clears out all those extra space-hogging replica copies. We've gone from storing double the amount of data to storing just our primary data plus one mathematically derived parity block. The space savings here are immediate and they are significant. And here is where the absolute magic of erasure coding happens. The rebuild process. Let's say a node completely dies and we lose data block C. Because we have our parity block P, the cluster doesn't panic. It simply takes the surviving data blocks A, B, and D, runs them against that parity block, and mathematically recalculates the exact contents of the missing block C. It rebuilds the missing data on the fly. Now keep in mind, this rebuild process does require read operations across the cluster, so your read performance can be temporarily affected during a rebuild depending on your strip size and current workload, but the data is safe. Of course, to do this complex math across distributed nodes safely, we have strict infrastructure minimums. You'll definitely see this on the exam. If you're running replication factor 2, erasure coding requires a strict minimum of 4 nodes, or 4 blocks, to maintain block awareness. But if you want the higher resiliency of replication factor 3, your minimum footprint jumps up. RF3 requires a minimum of 6 nodes or blocks to maintain block awareness for EC. Lock those numbers in right now. RF2 equals 4, RF3 equals 6. Looking at the numbers we've pulled straight from the Nutanix documentation, you can see how this builds out across different awareness levels. Notice how a desired awareness of node with a 1n/1d fault tolerance perfectly aligns with our 4-node minimum. If you want 2n/2d tolerance, meaning you can survive 2 simultaneous failures, you literally must have at least 6 nodes. The exact same logic scales up whether you're designing for node, block, or rack awareness. But actually, here's the golden rule you absolutely must remember for the exam. You have to ensure your cluster size is at least 1 node greater than the combined strip size, meaning your data plus your parity. Why? To allow actual physical space to rebuild the strips if a node fails. Think about it. If you size your cluster exactly to the strip size and a node dies, you won't have anywhere to put the rebuild data. Always plan for that n+1 capacity for rebuilds. Which brings us to Section 3, Exam Traps and Edge Cases. Okay, picture this, classic NCP-MCI exam scenario. You've got a functioning cluster, erasure coding is already enabled, it's purring along, saving you tons of space. Then your management decides, hey, we want to increase our resiliency. So you go into the console and enable rack awareness, or you raise the cluster fault tolerance. What actually happens to your erasure coding when you make that post-configuration change? Well, the answer is, it's highly disruptive. If rack awareness or a higher fault tolerance is enabled on a cluster that already has EC running, the cluster might actually need to reduce the EC strip size to comply with that new, stricter fault tolerance. To pull this off, AOS literally has to unpack the existing EC strips. This leads to an immediate temporary spike in storage space usage as data is re-replicated. Once the unpacking is finally done, it repacks the EC strips at the new, smaller size. And because the strip size is smaller, it's inherently less efficient. So after the repacking is complete, some amount of your original capacity savings will be permanently lost. It's a huge architectural gotcha, so watch out for it. Here is another absolute rule, and it's a perfect true-false exam trap. Erasure coding and deduplication are not supported if your cluster fault tolerance is configured for 1n and 1d. Let me just repeat that for emphasis. EC and dedup are totally unsupported with 1n and 1d cluster fault tolerance. If you see an exam scenario proposing this setup, flag it immediately as invalid. The math and the resiliency overhead simply do not allow it. Now, what if you want to evaluate if EC is even right for your data in the first place? You'd run the NCC health check called EC enablement check. This check looks at your storage containers and recommends whether EC would actually yield significant savings. But there is a catch here, and the magic number is 2. Erasure coding is an asynchronous process, right? Calculating those potential savings relies on analyzing the coldness of your data over time. Because of that, the EC enablement check requires a minimum of exactly 2 full curator scans to accurately calculate and display your potential savings. If you just set up a cluster and run the check immediately, it won't have the historical data it needs. You absolutely must wait for 2 full curator scans. Let's wrap this up with Section 4, Key Facts to Memorize. All right, rapid fire time. Lock these 4 key takeaways into your brain for test day. First, know your minimums. RF2 needs 4, but RF3 requires a minimum of 6 nodes or blocks to keep block awareness. Second, remember the efficiency stack. EC savings do not replace, but rather stack right on top of your deduplication and compression savings. Third, watch out for the unsupported CFT. EC and dedup are strictly unsupported with a 1 and 1D cluster fault tolerance. And finally, patience is key. The EC enablement check requires a minimum of 2 full curator scans before it can accurately recommend anything. So to finish up this explainer, I want to leave you with a real-world question to apply to your daily admin life. Based on these strict constraints regarding node minimums, fault tolerance changes, and curator scans, how are you going to evaluate your own cluster's readiness for erasure coding tomorrow morning? Look at your current RF, look at your CFT, and ask yourself, is turning on EC a simple click, or is it a full-blown architectural project? Thank you so much for joining me for this deep dive into NCP-MCI 7.5 erasure coding. Keep studying, trust the architecture, and I'll see you in the next explainer.